September 7th, 1942. Neville Island, Pennsylvania. A crowd of over 10,000 spectators lined the muddy banks of the Ohio River, climbing trees and perching on factory roofs to witness something that shouldn't have been possible. At 12:17 in the afternoon, a ship longer than a football field began sliding down greased launch rails into brown river water. The wake was so massive that people scrambled up the embankment, laughing and shouting as spray reached the shore. This was LST-1, the first landing ship tank built in America's heartland, 328 feet of welded steel that had been assembled in a Pennsylvania cornfield, 700 miles from the nearest ocean. Traditional maritime wisdom said you couldn't build ocean-going warships this far inland. Traditional maritime wisdom said a lot of things that were about to be proven catastrophically wrong. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The ship itself represented an impossible demand. Winston Churchill had called for vessels that could cross the Atlantic, beach themselves on enemy shores, and disgorge entire tank battalions directly onto hostile beaches. The Royal Navy's initial attempts had produced compromises, ships that were either ocean-worthy but couldn't beach properly, or could beach but couldn't survive ocean crossings. By November 1941, when British Admiralty representatives met with the United States Navy's Bureau of Ships, the strategic mathematics were brutal. Germany controlled the European coastline from Norway to Spain. Japan was sweeping across the Pacific. Any invasion would require putting heavy armor directly onto defended beaches, and there were no ships capable of doing that in sufficient numbers. Naval architect John Niedermayer sketched a rough design in that November meeting. A flat-bottomed vessel with bow doors, capable of shallow draft for beaching but with ballast tanks for ocean stability. The British approved it immediately, not because it was elegant, but because it was the only option that might work. By June 10, 1942, the keel of the first LST was laid at Newport News, Virginia. The program enjoyed the highest priority. The laid keel of an aircraft carrier was hastily removed from a building dock to make room for multiple LSTs. Congress authorized construction in 3 separate emergency acts. The ships were needed desperately, and they were needed yesterday. Enter the Dravo Corporation, a Pittsburgh company that had spent 50 years building barges, towboats, and river vessels. They had never constructed an ocean-going warship. Their Neville Island facility sat on the Ohio River, accessible only through inland waterways that would require navigating dozens of bridges to reach the Gulf of Mexico. Traditional coastal shipyards dismissed the idea as absurd. Admiral S.M. Robinson, chief of the Bureau of Ships, approached Dravo chairman J.D. Berg anyway. The conversation was brief. The Navy needed LSTs faster than coastal yards could produce them. Dravo had access to Pittsburgh's steel mills, a skilled workforce experienced in welding, and facility space that could be converted rapidly. Could they build ocean-going landing ships? Berg's answer came in January 1942. Dravo would build them, not just a few, but dozens. And they would do it using techniques that would horrify every traditional shipbuilder on the East Coast. The Neville Island yard underwent complete transformation in less than 4 months. Where there had been barge assembly areas, massive steel fabrication shops emerged. Where there had been small cranes for river work, gantry systems capable of lifting 150-ton sections rose into position. 5 separate fabrication plants scattered across Pittsburgh began producing prefabricated LST sections, steel modules that would be transported to Neville Island for final assembly. This was the heresy that maritime traditionalists couldn't accept. Ships were supposed to be built in place, piece by piece, from keel to superstructure in careful sequence. Dravo proposed building them in sections simultaneously across multiple facilities, then welding those sections together like assembling a massive steel puzzle. The prefabrication approach seemed to violate everything naval architects knew about hull integrity and structural stress. Welding, not riveting, would join the sections. This alone represented a leap of faith that made many Navy inspectors deeply uncomfortable. Riveted ship construction had worked for a century. Each overlapping steel plate was joined by thousands of heated metal pins, hammered into place by skilled crews who could install perhaps 100 rivets per day. A traditional ship required roughly 1 million rivets. Each rivet was a discrete connection, and each connection was a potential failure point, but also a crack arrestor. If one plate failed, the crack stopped at the riveted seam. Welded construction eliminated those natural barriers. A continuous weld meant a crack could propagate the entire length of a ship without stopping. The British Royal Navy forbade welded construction on warship hulls for exactly this reason. Yet WWII was proposing to weld every joint on vessels that would be driven onto hostile beaches, repeatedly grounded, and subjected to stresses no traditional ship encountered. The first challenge emerged immediately. Nobody in Pittsburgh knew how to weld hull sections for ocean-going ships. WWII's experienced welders understood river barge work, thinner plates, and lighter structures that never saw ocean waves. LST hull plates were thicker, the welds more critical, and the quality requirements far more stringent than anything they had attempted. In February 1942, WWII established welding schools within the yard. Experienced welders from pipeline construction and bridge building became instructors. Women, previously excluded from welding work entirely, were recruited by the thousands. Advertisements in Pittsburgh newspapers promised wages 20% above standard industrial rates and training that would take weeks, not years. The training itself represented another break from tradition. Master welders in coastal shipyards spent 4 years as apprentices learning comprehensive skills across all aspects of ship construction. WWII's program taught specific techniques for specific tasks in approximately 2 weeks. A worker didn't need to know how to weld everything, only how to weld vertical hull seams or horizontal deck plates or curved bow sections. They would perform that single task repeatedly, hundreds of times, achieving speed and consistency through specialization rather than broad expertise. By May 1942, WWII employed over 10,000 workers at Neville Island. Fewer than 200 had any previous maritime experience. The workforce included former housewives, farmers, factory workers, and teenagers fresh from high school. They worked in 3 shifts, 24 hours per day, 7 days per week. Office buildings, cafeterias, medical facilities, and parking lots were constructed around the expanding yard. The Navy Department built 5 miles of modern 4-lane highway and an auxiliary bridge across the Ohio River just to get workers to and from the facility. The prefabrication process that emerged was unlike anything traditional shipyards practiced. 5 fabrication plants scattered across Pittsburgh's industrial zone, each specialized in specific LST components. One plant built bow sections, complete with massive hinge doors and ramp mechanisms. Another produced stern sections, including rudder assemblies and propeller shafts. A third manufactured the enormous cargo deck sections, flat expanses of steel that would become the tank deck. Frame sections, bulkheads, and superstructure components came from dedicated facilities. Each prefabricated section was constructed according to carefully specified sequences. Welders started at the geometric center of each plate assembly and worked outward in spiral or radial patterns. This wasn't arbitrary. Someone had recognized that welds created residual stress as they cooled, and that stress needed to be managed, not concentrated. The sections were built small enough that the center outward pattern allowed stress to dissipate toward the edges rather than accumulate in the middle. After every series of welds, sections went into heat treatment ovens. These massive furnaces, each capable of holding a 30-foot steel assembly, heated the welded sections to 1100 degrees Fahrenheit and cooled them slowly. The process, called stress relief annealing, allowed the steel's internal structure to relax. Residual welding stresses that would normally be locked into the metal permanently were dissipated before the sections ever left the fabrication plant. Traditional shipyards didn't stress relieve anything. The idea of heating massive ship sections in ovens seemed absurdly expensive and time-consuming. But WWII's engineers had learned something from pipeline construction across temperature extremes. Steel that underwent stress relief didn't crack. Steel that carried locked-in residual stress failed catastrophically when subjected to temperature changes and repeated flexing. If LSTs were going to survive being repeatedly beached, hauled off, and driven through ocean swells, they needed steel that could handle that punishment. The transportation system feeding Neville Island became a logistical ballet. Railroad tracks crisscrossed the facility, moving sections from fabrication plants to assembly positions. Flatbed trucks carried components through Pittsburgh's streets at night when traffic was minimal. Barges transported the largest sections down the Monongahela River to the Ohio. At peak production, over 300 separate prefabricated components arrived at Neville Island daily, each one arriving exactly when the assembly sequence required it. Assembly on the building ways followed a radically compressed timeline. Traditional shipyard practice started with the keel, building upward layer by layer over months. Each section waited for the previous section to be complete before work could begin. Dravo's approach assembled major components simultaneously. While welders joined bow sections at one end of the building way, other crews positioned stern sections at the opposite end. Engine room modules, constructed as complete units in separate facilities, were lifted by massive cranes and lowered into position in single operations. Cargo hold sections, each one a 30-foot module of welded steel frames, were positioned in sequence like building blocks. The welding that joined these major sections required extraordinary precision. Gaps between components had to align within tolerances of less than 1/8 of an inch across joints spanning 50 feet. Temporary bolts held sections in position while welders completed permanent seams. Quality inspectors examined every joint before allowing work to proceed. This wasn't just obsessive perfectionism. Misaligned joints created stress concentrations, points where structural loads would accumulate rather than distribute evenly. Those stress concentrations would become crack initiation sites when the ship encountered the real world. September 7th, 1942, at 12:17 in the afternoon, LST-1 slid into the Ohio River after weeks of assembly. The launch generated enormous local interest. Radio broadcaster Lowell Thomas, one of America's most famous voices, described the moment live. It was an ocean-going ship, built for Uncle Sam's Navy, built out here at Pittsburgh and launched here at Pittsburgh. A ship of steel, 328 feet long. The most interesting thing about it is that this sea-going vessel launched here in the Ohio River came off an assembly line. That phrase, came or off an assembly line, captured what made traditional maritime authorities so uncomfortable. Ships were supposed to be craft, not manufactured products. They were supposed to emerge from the hands of experienced shipwrights who understood the sea's demands. The idea that ships could roll off production lines like automobiles seemed to cheapen the entire profession. It also seemed impossible that such ships would survive actual naval service. LST-1 began her journey to the Gulf of Mexico on September 10, 1942. The voyage down the Ohio and Mississippi rivers required careful navigation past dozens of bridges. Some bridges were high enough for clearance. Others required the Navy's specially established ferry command to coordinate temporary modifications. In several locations, bridge spans were temporarily raised or removed to allow passage. The 700-mile journey took 2 weeks. When LST-1 reached the Gulf, naval inspectors conducted exhaustive sea trials, searching for the inevitable failures that would vindicate traditional shipbuilding wisdom. The ship performed flawlessly. Hull integrity underway was excellent. Ballast systems allowed transition from deep draft for ocean travel to shallow draft for beaching exactly as designed. The bow doors and ramp mechanism functioned properly. Engine performance met specifications. Most critically, after repeated beaching tests that deliberately stressed the hull in ways no traditional ship encountered, stress inspections revealed the welded joints held without cracking. The prefabrication approach, the welding sequences, the stress relief treatment, all of it worked. LST-1 was commissioned on December 14, 1942, and assigned to the Pacific Theater. She would eventually earn 4 battle stars, participating in landings at Salerno, Anzio, and Normandy before the war ended. But while LST-1 was proving her seaworthiness, something more profound was happening back at Neville Island. Dravo wasn't content with simply building LSTs. They were refining the process with every hull, learning what worked and what created bottlenecks, optimizing sequences, and improving quality. By October 1942, Dravo employed 16,000 workers. Production had accelerated beyond what Navy planners thought possible. The challenge then became, how fast could this process actually go? The assembly line theory said that repetitive processes improved with practice. Workers became faster and more skilled. Bottlenecks were identified and eliminated. Material flow was optimized. Equipment was upgraded. Dravo's production statistics demonstrated this learning curve with remarkable precision. The first LST required approximately 133 days from keel laying to commissioning. By early 1943, construction time had dropped to roughly 90 days. By mid-1943, it was down to 60 days. Each ship was completed faster than the last. Traditional shipyards watched this acceleration with a mixture of awe and horror. It shouldn't have been possible to build ocean-going warships this fast. The very concept violated everything maritime engineers believed about the time required for proper construction. Yet Dravo kept shortening the timeline while maintaining quality that met or exceeded Navy specifications. The ships weren't beautiful by traditional standards. LST crews called them large, slow targets because of their 11-knot maximum speed and considerable bulk. But they were functional, they were reliable, and most importantly, they existed in quantities that were beginning to matter strategically. By November 1943, Dravo had launched over 50 LSTs. American Bridge Company in Ambridge, Pennsylvania, using techniques pioneered by Dravo, had launched dozens more. 4 other inland shipyards along the Ohio and Mississippi rivers had converted facilities for LST production, all using prefabrication and welding methods that Dravo developed. The Cornfield Navy, as these inland yards were mockingly called, was producing 2/3 of America's entire LST fleet. Then came the challenge that would push the entire system to its absolute limit. In April 1944, Secretary of the Navy James Forrestal visited Neville Island with an urgent request that bordered on impossible. The invasion of Normandy was scheduled for early June. The operation required more LSTs than were currently available. Allied planners were desperately short of landing craft, so short that the invasion had already been delayed from May to June to allow more vessels to be completed. Forrestal needed 15 additional LSTs delivered by May 31st. That gave Dravo 60 days to build 15 ships that normally took 60 days each to construct. The math was simple and brutal. Impossible under any conventional understanding of shipbuilding, yet strategically essential. The fate of the entire European invasion timetable potentially rested on whether a Pittsburgh shipyard could accomplish something that violated every assumption about production capability. The request triggered what Dravo called the hot ship program. Every resource, every optimization, every efficiency that had been discovered over 2 years of LST production would be pushed to its absolute maximum. Workers volunteered for extended shifts. Assembly schedules were compressed to their theoretical limits. Material deliveries were prioritized above everything else, flowing through Pittsburgh's industrial complex. The prefabrication plants operated at maximum capacity, producing sections in parallel for multiple hulls simultaneously. The stress was enormous. Workers understood what was at stake. Men were training for the invasion in England. Transport ships were loading equipment. Entire divisions waited for the ships that would carry them across the English Channel. If the LSTs didn't arrive on schedule, soldiers would die unnecessarily, or the invasion would be delayed again, giving Germany more time to fortify the Atlantic Wall. The pressure to deliver was literal and existential. By mid-May 1944, all 15 ships were simultaneously under construction at Neville Island. The yard had never attempted to build this many vessels in parallel. Assembly ways that normally held 2 or 3 hulls now held 5 or 6 at various stages of completion. Cranes moved continuously. Welders worked back-to-back shifts. Inspectors checked quality while work proceeded around them. The entire facility operated at a tempo that seemed unsustainable. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. May 29, 1944. The 15th LST slid down the launch rails into the Ohio River. Forrestal's deadline was May 31st. Dravo delivered with 2 days to spare. 15 complete LSTs, each one built to full Navy specifications, each one passing rigorous inspection, completed in 60 days. The average construction time for each vessel, exactly 3.5 days from start of assembly to launch. The number seemed incomprehensible. 3.5 days to build a ship longer than a football field. 3.5 days to weld together hundreds of prefabricated sections into a vessel that would carry 20 Sherman tanks and 160 soldiers across the Atlantic, drive onto a defended beach under fire, and survive the experience. Yet the ships were real. They sailed to the Gulf, underwent trials, and were commissioned for service. And when June 6, 1944 arrived, and the largest amphibious invasion in history began, those Pittsburgh-built LSTs were there. Of the 173 LSTs that participated in the Normandy landings, at least 53 were built in Pennsylvania. They beached on Omaha and Utah beaches, their bow doors opening to disgorge tanks and trucks and supplies directly onto French sand. German artillery targeted them. Some were hit. LST-262, built at American Bridge's Ambridge facility, served at Normandy before being torpedoed and sunk off the southern coast of France in August 1944. But most survived, made multiple trips across the Channel, and continued operating for months afterward. The strategic impact was incalculable. Without sufficient LSTs, the Normandy invasion might have failed or been delayed indefinitely. With them, the Allies put ashore 130,000 troops within 48 hours, followed by 250,000 vehicles and 5 million tons of supplies over the next 2 months. This wasn't done through ports, which remained damaged or heavily defended. This was accomplished through landing craft, driving directly onto beaches, unloading, and returning for more cargo. The LSTs made it possible. Yet the story of how these vessels were built so impossibly fast remained obscure, buried in production statistics and Navy reports. The prefabrication techniques, the welding sequences, the stress relief protocols, all of it worked, but why it worked wasn't fully understood even by the engineers implementing it. Traditional shipbuilders assumed Dravo was simply lucky, or cutting corners that would reveal themselves later through structural failures. The uncomfortable truth was more subtle and more damning to established practice. The answer to why Dravo succeeded where traditional methods failed lay not in grand engineering breakthroughs, but in observations from the welding floor itself. The kind of practical knowledge that comes from watching steel behave under torches night after night, accumulated by workers who weren't supposed to question engineering decisions but did anyway. Among the thousands of welders at Neville Island and the surrounding fabrication plants, patterns emerged that contradicted what naval architects assumed about ship construction. Traditional riveted ship construction had developed over centuries of trial and error. Overlapping plates joined by mechanical fasteners created natural discontinuities in the hull structure. Each riveted seam was a potential weak point, but also a crack arrestor. If a crack initiated in one plate, it would travel to the riveted joint and stop, unable to propagate into the adjacent plate because the connection was mechanical, not metallurgical. Ships built this way could sustain local damage without catastrophic propagation. Welded construction eliminated those barriers. A continuous weld created a metallurgical bond, essentially making multiple plates into a single continuous structure. The efficiency was obvious. Welding was faster than riveting, required fewer workers, and created lighter structures without the added weight of overlapping plates and thousands of rivets. But the vulnerability was equally clear. A crack in welded structure could propagate continuously across joints that would have stopped it in riveted construction. What nobody fully understood in 1942 was that the welding process itself was introducing massive residual stresses into the hull structure. When a welder runs a torch along a seam, the localized temperature exceeds 2500 degrees Fahrenheit. The metal in the heat zone expands dramatically. As the weld cools and solidifies, it contracts, but the surrounding cold steel constrains that contraction, locking tensile stress into the weld and the adjacent material. That stress becomes permanent unless something is done to relieve it. The scale of these residual stresses was staggering. Measurements that would later be taken on traditionally constructed welded structures showed residual tensions exceeding 30,000 pounds per square inch, concentrated at key structural points. This was stress that existed even when the ship was sitting calmly at dock, before any external loads were applied. When those ships encountered actual service conditions, cold water, repeated flexing, impact stresses, from grounding, the residual stress combined with applied loads to create conditions where catastrophic fracture became not just possible but probable. Liberty ships, those mass-produced cargo vessels that Kaiser's West Coast yards were building at record speed, were experiencing exactly this problem. Between 1943 and 1944, more than 1,500 Liberty ships reported serious structural cracks. At least 19 vessels broke completely in half, some while tied safely at dock. 3 simply vanished at sea, disintegrating so rapidly they couldn't send distress signals. The steel wasn't defective, the welds weren't poorly executed. The fundamental problem was residual stress locked into the structure by welding sequences that concentrated stress rather than managing it. Yet LSTs weren't experiencing these failures. Despite being subjected to far more brutal treatment than cargo ships, repeatedly beached and hauled off through surf that flexed their hulls in ways Liberty ships never encountered, the LSTs weren't cracking. This discrepancy puzzled naval architects through 1943 and into 1944. Liberty ships used similar steel specifications, similar welding techniques, and were built with equal care. Why were they fracturing while LSTs remained intact? The answer was in the welding sequences, though it would take years before anyone fully understood why those sequences mattered so critically. WWII's fabrication plants had adopted a practice that seemed inefficient to traditional shipyard supervisors, welding from the center of sections outward in carefully prescribed patterns. This wasn't standard practice. Conventional wisdom said to start at one edge and work across, or to complete one section entirely before moving to the next. Those approaches were faster in the short term because workers didn't have to constantly reposition themselves or think about sequence. But someone at WWII, likely multiple people working independently, had observed that welds executed in traditional sequences caused visible warping in the steel plates. Hull sections would distort as cooling welds contracted, pulling the metal into stressed configurations. When these stressed sections were then welded to other sections, the accumulated stress became locked into the hull permanently. The result was a structure carrying millions of pounds of internal tension before it ever touched water. The center outward welding sequence did something fundamentally different. By starting each plate assembly at its geometric center and working toward the edges in a balanced pattern, the method allowed residual stress to dissipate as it formed. Each new weld created stress, but that stress could flow toward the edges of the section where it encountered free boundaries rather than accumulated in the center. The sections still carried some residual stress, but it was distributed across broader areas rather than concentrated at specific points. The heat treatment ovens completed what the welding sequence started. Heating welded sections to 1100 degrees and cooling them slowly allowed the steel's crystalline structure to relax. Stress that had been locked into the metal during welding was released as the steel was brought above its transformation temperature and allowed to re-equilibrate. When the sections cooled slowly in controlled conditions, they retained their shape but shed the dangerous internal tensions that would have become crack initiation sites. This combination, sequenced welding plus stress relief heat treatment, wasn't documented in any naval architecture textbook. It emerged from practical observation and was implemented because it produced sections that lay flat and true rather than warped and stressed. The theoretical understanding of why it worked would come later, after metallurgists examined failed Liberty ships and intact LSTs and recognized the difference in residual stress levels. The prefabrication approach amplified these benefits in ways that weren't immediately obvious. By building LSTs in small sections that could be completely welded and stress-relieved before assembly, WWII was creating hull components that started from a relaxed state. When these sections were joined into the complete hull, only the final assembly welds introduced new residual stress, and those could be managed through careful sequencing of the joining operations. Traditional shipyards building ships in place from keel upward accumulated stress continuously throughout construction. Each day's welding added more stress to a structure that already carried yesterday's locked-in tensions. By the time the hull was complete, it was a complex three-dimensional stress field, with concentrations at corners, penetrations, and structural transitions. Those concentrations were fracture initiation sites, waiting for the right conditions to fail. LSTs, despite being driven onto beaches repeatedly, didn't provide those conditions. The hull design itself contributed to their success. The flat bottom and the wide beam distributed grounding loads across a large area rather than concentrating them on a keel. The structural frames were closely spaced, providing redundancy. But most critically, the low residual stress in the hull meant that applied loads from grounding didn't combine with existing internal stress to exceed the steel's capacity. The proof emerged not through laboratory testing, but through operational experience. By mid-1944, over 600 LSTs were in service across both theatres. They were being driven onto coral reefs, sandy beaches, rocky shores, mud flats, and every other type of hostile landing environment imaginable. They were sustaining battle damage from artillery, bombs, and torpedoes. They were operating in Arctic waters off Alaska and tropical waters in the South Pacific. They were being subjected to every stress condition that could test a ship's structural integrity. And they weren't breaking. Minor cracks appeared occasionally, stress concentrations that inspection caught early. Those were repaired using the same sequenced welding and stress relief procedures, and the ships returned to service. But catastrophic hull failure, the kind that was plaguing Liberty ships, simply didn't occur in LSTs. The failure rate from structural problems was effectively zero across over 1,000 vessels built. This operational success validated WWII's methods in a way that no amount of engineering analysis could have. The ships worked. They survived conditions that should have broken them according to traditional understanding. And they did it because the construction process had accidentally stumbled upon principles of residual stress management that the formal engineering establishment hadn't fully recognized. The illegal aspect of the title deserves explanation. There was nothing literally unlawful about WWII's methods, but they violated the unwritten rules of shipbuilding traditions so thoroughly that to traditional maritime engineers, they seemed almost criminally reckless. Building ships in cornfields 700 miles from the ocean violated every assumption about where ships should be constructed. Welding instead of riveting violated preferences that had Royal Navy endorsement. Prefabricating sections rather than building in place violated centuries of practice. Training workers in weeks rather than years violated guild traditions about skill development. Every aspect of WWII's approach was heretical to established practice. That it worked, and worked better than traditional methods, was the most damning evidence possible that tradition had been wrong about fundamental principles. The trick wasn't a trick at all. It was systematic application of sound engineering principles that happened to contradict conventional wisdom. The scale of production that this approach enabled became strategically decisive. By June 1944, American yards had completed over 800 LSTs. Of those, 670 came from the 5 inland shipyards that used WWII's techniques. 2/3 of America's entire LST fleet was built using methods that the maritime establishment had initially dismissed as impossible. Those ships made the difference between invasion plans that were logistically feasible and plans that remained theoretical exercises. Consider the arithmetic of amphibious warfare. Each LST could carry 20 Sherman tanks or equivalent cargo. To land a single armoured division required approximately 40 LSTs in the first wave, followed by continuous resupply waves. The Normandy invasion involved multiple divisions across multiple beaches. The mathematics required hundreds of LSTs operating simultaneously, with more in reserve for follow-on operations and inevitable losses to enemy action or weather. Traditional shipbuilding methods, even at their most efficient, couldn't produce LSTs fast enough to meet these requirements. Coastal yards using conventional techniques took 4 to 6 months per vessel. At that rate, building the 800 LSTs available by D-Day would have required years. The invasion would have been delayed into 1945 or later, giving Germany more time to fortify defences and develop weapons that might have made invasion impossible. Dravo's methods compressed that timeline by factors that seemed impossible until they were demonstrated. 3.5 days per ship during the hot ship program represented the absolute peak of optimization, but even the normal production rate of 60 days per ship was a revolution compared to traditional practice. This acceleration made the difference between an invasion that could happen in 1944 and one that might never happen at all. The human cost of these production achievements played out across 2 oceans through 1944 and 1945. LST-282, built at American Bridge in Ambridge, participated in the Normandy landings, making multiple trips across the Channel before being torpedoed and sunk off southern France in August 1944. Her crew had time to evacuate. 23 men died, but 79 were rescued. The ship's structural integrity, even after torpedo damage, gave them those extra minutes that meant the difference between survival and death. LST-531 hit a mine off Utah Beach during the Normandy invasion. The explosion tore a massive hole in her bow, flooding the tank deck. In a Liberty ship, that kind of damage typically led to catastrophic crack propagation and rapid sinking. LST-531's welded hull contained the damage. The crack didn't propagate beyond the immediate blast zone. She stayed afloat long enough for her crew to beach her, and most survived. The ship was later repaired and returned to service. LST-47, built at Dravo's Neville Island yard, made 17 round trips across the English Channel between D-Day and the end of August 1944. Each trip involved beaching under fire, unloading while exposed to artillery, and hauling off through surf that flexed the hull through stress cycles that would have fractured conventionally built ships. She completed all 17 missions without significant structural problems, carrying thousands of tons of supplies and evacuating hundreds of wounded soldiers. The reliability of these vessels under extreme conditions represented validation that exceeded anything laboratory testing could provide. Ships that worked in theory often failed in practice. Ships built at impossible speed by inexperienced workers using unconventional methods should have been death traps. Instead, they were among the most survivable vessels in the entire amphibious fleet. Crews learned to trust them in ways they never trusted earlier landing craft. The psychological impact on sailors and soldiers mattered enormously. Men who had to ride into combat aboard these ships needed confidence that the vessel wouldn't disintegrate beneath them before they reached the beach. Early landing craft had been notoriously fragile. Stories circulated of boats that sank from mechanical failure or structural damage before reaching shore. LST crews developed a different reputation. The ships were slow, ungainly, and uncomfortable, but they got you there and they got you back. That reliability was worth more than speed or elegance. By August 1945, when the war ended, over 1,050 LSTs had been commissioned. They had participated in every major amphibious operation in both theatres: Sicily, Salerno, Anzio, Normandy, southern France, the Gilbert Islands, the Marshalls, the Marianas, Peleliu, Leyte, Luzon, Iwo Jima, Okinawa. 343 LSTs supported the Okinawa invasion alone, the largest amphibious operation in the Pacific War. They had transported millions of tons of cargo, hundreds of thousands of troops, and tens of thousands of vehicles directly onto hostile shores. The casualty rate among LSTs was remarkably low given their exposure. 26 were lost to enemy action, torpedoes, bombs, mines, and artillery. 13 were lost to weather, accidents, or mechanical failure. A few additional ships were damaged beyond repair. Out of over 1,000 vessels built, the total loss rate was under 4%. This compared favorably with every other ship type that saw combat, and was extraordinary for vessels that deliberately drove themselves onto beaches under fire. The few catastrophic failures that did occur revealed the limits of even well-executed welding. LST-353 was destroyed by internal explosion while moored at Pearl Harbor in May 1944. The blast was so violent that it effectively vaporized the ship. No welding sequence or stress relief protocol could have saved her. 6 LSTs were lost on a single day in 1943 when an ammunition explosion at a supply depot detonated cargo aboard ships moored nearby. These were losses to munitions, not structural failure. The longevity of surviving LSTs provided the ultimate vindication of construction quality. These were ships designed as emergency vessels with expected service lives of perhaps 5 years. Many remained in service for decades. USS LST-325, built in 1942, is still operational as a museum ship in Evansville, Indiana, as of 2025. The ship is 83 years old and has crossed the Atlantic under its own power in the 21st century. That a vessel built in weeks using techniques that were considered experimental in 1942 could survive 8 decades of existence speaks to the fundamental soundness of the methods. The Korean War saw extensive LST service, with many of the same World War II vessels participating in the Incheon landings. They were older, slower, and more obsolete by 1950, but they still worked. The Vietnam War saw another generation of LST service. Even into the 1990s, LST principles influenced amphibious warfare doctrine and ship design. The modern dock landing ships that carry Marines into combat are direct descendants of those Pittsburgh-built vessels, incorporating lessons learned from 8 decades of amphibious operations. The technical legacy of Dravo's LST construction methods extended far beyond naval architecture. The principles of residual stress management through welding sequence and heat treatment became foundational to every welded structure built after World War II. Bridge construction, pressure vessel fabrication, pipeline installation, offshore oil platforms, power plant components, every application where welded steel structures encountered stress or temperature extremes incorporated lessons that emerged from the urgency of wartime ship production. The American Welding Society's Structural Welding Code, first published in 1947, codified center-outward welding sequences and stress relief requirements as mandatory standards for critical structures. These weren't presented as innovations from LST construction, but as discovered principles of sound engineering practice. The origin stories were sanitized, attributed to laboratory research and engineering analysis, rather than observations from shipyard welding floors. But the timing was unmistakable. The code appeared within 2 years of war's end, incorporating practices that had been proven by thousands of ships built under emergency conditions. Pipeline construction across Alaska in the 1970s explicitly referenced welding procedures developed during World War II ship construction. The Trans-Alaska Pipeline, 800 miles of welded steel carrying hot oil through sub-zero temperatures, exists because engineers understood the lessons about cold weather cracking and residual stress that LST construction had demonstrated. The pipeline used sequenced welding, stress relief protocols, and quality inspection procedures that were direct descendants of methods developed at Neville Island 30 years earlier. Bridge engineering underwent similar transformation. The catastrophic failure of the Point Pleasant Bridge in West Virginia in December 1967, which killed 46 people, included residual welding stress as a contributing factor. The investigation revealed welds executed without proper sequencing had locked stress concentrations into structural members that then failed under load. Post-disaster code revisions mandated the sequencing and inspection protocols that World War II ship construction had pioneered. Every welded bridge built since incorporates those requirements, though few engineers know their origin. The offshore oil industry learned these lessons repeatedly, always at terrible cost. The Alexander Kielland platform disaster in Norway in 1980, where 123 workers died when the platform capsized, traced partially to fatigue cracks propagating from improperly sequenced welds. The Piper Alpha platform explosion in 1988, killing 167 men, began with a crack in a welded pipe connection that had accumulated residual stress. Each disaster prompted investigators to examine welding procedures, and each investigation rediscovered principles that LST construction had proven 40 years earlier. Nuclear reactor pressure vessels represent the ultimate application of these principles. The massive steel shells enclosing reactor cores under extreme temperature and pressure cannot tolerate any crack initiation points. Welding sequences for reactor vessels are planned with computational precision, simulating thermal effects and residual stresses before the first weld is struck. The entire vessel receives post-weld heat treatment in enormous ovens, eliminating residual stresses that could become failure points. The engineers designing these procedures in the 1950s explicitly studied World War II ship construction as their foundational reference, though they rarely acknowledged that Cornfield shipyards in Pittsburgh had pioneered the methods. The democratization of skilled work that LST construction enabled had implications that extended beyond shipbuilding. By proving that complex manufacturing could be performed by workers trained in weeks rather than requiring generational craft expertise, Dravo's program challenged fundamental assumptions about labor, skill, and industrial organization. The post-war economy absorbed hundreds of thousands of workers who had learned industrial skills in emergency training programs. Women who had welded hull plates went into manufacturing. Men who had operated cranes became construction workers. The skills were transferable, and more importantly, the confidence that came from accomplishing something previously considered impossible was transformative. The workers themselves carried those lessons forward into peacetime careers. A woman who had welded ship sections on night shift at age 22 didn't accept being told that women couldn't do industrial work when she was 30. A black man who had operated million-dollar crane systems moving 100-ton loads didn't accept being relegated to unskilled labor positions after the war. The wartime necessity that had opened opportunities created expectations that peacetime employers couldn't simply close off again. The social changes that followed weren't directly caused by LST construction, but the experience of demonstrating capability under pressure contributed to broader transformations in American labor and civil rights. The engineering establishment's response to these wartime achievements was complex and revealing. On one hand, the success of unconventional methods forced acknowledgement that traditional practice had been wrong about significant principles. The speed of construction, the quality of results, and the operational success of the vessels couldn't be denied. On the other hand, admitting that welders on production floors had observed things that naval architects with advanced degrees had missed was professionally uncomfortable. The solution was to reframe the discoveries in academic language. Residual stress management became a topic of research papers that made minimal reference to the practical observations that had led to the techniques. Welding sequence optimization was presented as derived from theoretical analysis rather than from watching steel warp under torches. The formal engineering literature incorporated the lessons while obscuring their origins, a pattern that repeated across multiple technical disciplines in the post-war years. The economic calculation of LST production revealed truths about manufacturing efficiency that challenged conventional assumptions about cost and quality. Each LST cost approximately $2 million to build using Dravo's methods. Traditional coastal yards estimated they would need $3 to $4 million per vessel using conventional construction. The cost difference wasn't just speed, it was systematic efficiency. Prefabrication eliminated waste. Parallel production used labor more effectively. Quality control in factory settings was more rigorous than on-site inspection. The faster construction actually produced better outcomes at lower cost, violating the traditional assumption that speed and quality were in opposition. This lesson influenced manufacturing across industries in the post-war era. The assumption that craftsmanship required time was replaced by understanding that well-designed processes produced consistent quality regardless of speed. just-in-time manufacturing, lean production, and other efficiency methodologies that dominated late 20th century industry, all incorporated principles that wartime shipbuilding had demonstrated. Parallel operations, modular assembly, statistical quality control, and rapid worker training on specific tasks rather than comprehensive apprenticeship. The strategic impact of LST availability on Allied operations cannot be overstated. Winston Churchill's famous comment that the destinies of two great empires seem to be tied up in some god-damned things called LSTs captured the reality that grand strategy was constrained by logistics more than by combat power. You could have the best trained troops, the most advanced weapons, and brilliant operational plans, but without ships to transport them to enemy shores, none of it mattered. The LST solved that constraint, and solved it in quantities that made multiple simultaneous operations possible. Consider the counterfactual. If LSTs had only been available from traditional coastal shipyards using conventional construction methods, the timeline would have been radically different. At 4 to 6 months per vessel, building 800 LSTs would have required 6 to 8 years of production, pushing completion dates into 1948 or later. The war would have ended differently, or not ended at all. The invasion of Europe might have been attempted using inadequate numbers of landing craft, resulting in catastrophic losses. Or it might have been postponed indefinitely while Germany developed atomic weapons or made separate peace with the Soviet Union. The fact that the invasion did happen in June 1944, that it succeeded despite horrific casualties, and that it led to Germany's defeat within 11 months was directly enabled by having sufficient LSTs. Those ships were available because a Pittsburgh company that had never built warships before figured out how to manufacture them faster than anyone thought possible. The shipyard workers who welded hull plates on night shift probably didn't think of themselves as shaping history. They were doing their jobs, earning wages, and hoping the war would end soon. But their work made possible operations that determined the outcome of the largest war in human history. The forgotten welder, whose name doesn't appear in any historical record, who observed that certain welding sequences produced less warping than others, who suggested starting at the center and working outward, who persisted even when supervisors dismissed the observation. That person changed the course of the war. Not through heroism or brilliance, but through careful attention to how steel actually behaves under heat and stress. The lesson is profound. Sometimes the most important innovations come from people who are close enough to the work to see what's really happening, rather than from experts who know what should be happening. The Pittsburgh shipyards shut down after the war ended. Dravo reduced its workforce from 25,000 to fewer than 2,000 by spring 1946. The Neville Island facility that had produced 145 LSTs was converted back to barge production. American Bridge's Ambridge yards, which had built nearly 200 LSTs, returned to structural steel fabrication for bridges and buildings. The launchways where ships had slid into the Ohio River were dismantled. The fabrication plants that had produced prefabricated sections closed or converted to peacetime production. By 1950, little physical evidence remained of the massive emergency program. The ships themselves were scattered across both oceans, many already in mothballs or sold for scrap. The workers had moved on to other jobs, other cities, other lives. The techniques they had pioneered were being incorporated into industry standards without attribution. The story of how cornfield shipyards revolutionized naval construction was fading from memory, overshadowed by more dramatic wartime narratives about combat and heroism. Yet the impact endured in ways both visible and invisible. Every welded structure that didn't fail because proper stress relief procedures were followed. Every bridge that didn't collapse because welding sequences were carefully planned. Every pressure vessel that contained explosive forces because residual stresses had been eliminated. Every pipeline that survived Arctic temperatures because the steel had been prepared correctly. All of them embodied lessons learned in the urgency of wartime production, when there was no time to get it wrong and no resources to waste on methods that didn't work. The workers who built these ships deserve remembrance not just for their contribution to victory, but for demonstrating capabilities that permanently transformed industrial practice. They were housewives who became welders, farmers who became crane operators, teenagers who became quality inspectors. They worked in conditions that were often dangerous, always demanding, and sometimes overwhelming. They did it without the benefit of decades of experience or traditional training. They did it by learning quickly, adapting constantly, and paying attention to what actually worked rather than what was supposed to work. The ships they built carried soldiers into combat, evacuated wounded from beaches, delivered supplies that kept armies fighting, and made possible operations that books and movies would commemorate for decades. But beyond that specific contribution, they proved something more fundamental about human capability, that complex things can be accomplished quickly when necessity demands it. That tradition is not always wisdom. That observation matters more than credentials. That dedicated people, properly organized and given clear goals, can achieve what experts declare impossible. LST-1, the first ship launched from Neville Island on September 7, 1942, was scrapped in 1961 after nearly 2 decades of service. She had crossed the Atlantic, participated in multiple amphibious operations, survived the war, and continued operating through the post-war years and Korea. When she was finally cut apart for scrap, the welded seams that had seemed so experimental in 1942 were still sound. The hull that had been assembled in weeks from prefabricated sections had lasted longer than most conventionally built ships. The proof was in the steel itself. The 72-hour construction timeline that gives this story its title represented the absolute peak of optimization, achieved only during the hot ship program under maximum urgency. It wasn't sustainable long-term, and it wasn't meant to be, but it demonstrated what was possible when every element of a production system was pushed to its theoretical limit. 3 days from start to launch for a 328-foot warship. The number still seems impossible, even knowing it happened, even seeing the documentation, even understanding the techniques. That impossibility is the point. What seems impossible today becomes routine tomorrow when enough people commit to making it happen. The maritime establishment said you couldn't build warships in cornfields. You could. They said welding wasn't reliable enough for hull construction. It was. They said workers needed years of training to build ships. They didn't. They said prefabrication would create weak structures. It created stronger ones. Every assumption was wrong, and proving them wrong required willingness to ignore conventional wisdom and discover what actually worked through trial and observation. The lesson extends beyond shipbuilding or manufacturing. It applies whenever established practice meets urgent necessity. Sometimes the experts are right, and tradition reflects accumulated wisdom. Sometimes the experts are wrong, and tradition reflects accumulated assumptions that were never properly tested. Distinguishing between wisdom and assumption requires being willing to try different approaches, to observe carefully what happens, and to adjust based on results rather than preconceptions. The welders at Dravo and American Bridge weren't trying to revolutionize industrial practice. They were trying to build ships fast enough to meet production schedules. The fact that their methods transformed construction practices across multiple industries was an unintended consequence of solving an immediate practical problem. This pattern, urgent necessity driving innovation that has broader impact than originally intended, repeats throughout technological history. The innovations that matter most often emerge from people trying to accomplish specific tasks, not from people trying to innovate abstractly. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.